In this section, we are going to be looking at the cell structure of a 6 transistor static RAM cell. SRAM 60 stands for static random access memory, 6 transistors. So this is what one SRAM cell with 6 transistors looks like. You have 1, 2, 3, 4, 5, 6 transistors. So we will first understand the circuit, the setup, and then we'll see how to perform a write operation and how to perform a read operation on this cell. So this line you see here is the voltage line. So the voltage supply runs through this part. So you have a transistor 1, a transistor 2, a transistor 3 and a transistor 4 which are connected in this fashion. Here is the grounding. Also we have a transistor 5 and a transistor 6 which are connected to the bit line and the bit complement line respectively, and then to capacitors C1 and C2. Now we will understand the function of each of these segments first and then we'll move on. So this entire part that you see here, this 4 transistor setup, it is equivalent to using 2 NOT gates connected in a loop. So this, as you know, is your normal logic complement gate. So if you connect 2 complement gates like this, and let's say you provide a value q as input at this point you would get q complement having passed through one NOT gate, and at this point having passed through another NOT gate you would get back q. So this is not a part of your SRAM setup, but let me first explain what this is and then I'll tell you why we're talking about this. So whatever value you give, this circuitry retains the same value on the left and gives you its complement on the right. So it sort of stores the value, it remembers the value. So if I've given a value as input, whenever I need that value back, all I need is to take it out from this part. So this is what this 2 inverter circuit does. And why we looked at that is because this entire 4 transistor setup does exactly the same job. So whatever input I give as Q will always be available to me on my left hand side, and its complement will always be available to me on my right hand side. So that is the innermost part of the setup. Now after that we have 2 transistors M5 and M6 which are called access transistors. So what do we mean by that? So in your memory, you know that your memory is an array of cells like this, right? This is the structure of one cell. So up to this. Yeah, so this is what one cell looks like, and your memory is going to be made up of millions of cells like this. So if I want to access the data from a particular cell, or if I want to write something onto a particular cell, I should first select that cell and then do whatever I want with it, right? So to select a particular cell, we use our M5 and M6, which is why they are called access transistors. So how exactly do we select? We'll see that soon, but for now know that M5 and M6 are used to select a particular cell from the array of cells that make up my memory, which is why they are called access transistors. And then we have the bit and bit complement lines. These are again binary values, 0 or 1. So if bit is 1, bit complement will be 0 and vice versa. And they act both as my input and output lines. So when I am reading a value, the value stored over here will travel through bit, or Q bar will travel through bit complement. When I am trying to write a value, I feed it through bit and it gets stored in Q, or if I feed it through bit complement, it gets stored in Q bar. So these 2 lines act both as input and output lines. So that is the basic structure of an SRAM 6 transistor cell. Now we will see first how to perform a read operation and then how to perform a write operation. So to perform a read operation, like I said, our bit and bit complement act as output lines. Whatever output is there, it travels either through B or B dash and comes. So the first step is to set the write line WL to 1. This line. This again is a binary value. It can take either 0 or 1. So if you pass current through this line, it is a high or a 1. If you don't, it is a low or a 0. So to read, we set this line to 1 first of all. And when we do that, these 2 transistors connected to this line get switched on. So meaning this cell is selected. So whatever I am going to do now will be done on this cell. So this is what I meant when I said selecting one cell from an array of cells. How do you select? You set the WL to be a high or a 1, thereby switching on these 2 transistors. indicating that any operation that is performed now will be performed on this cell. That is our first step. Second step, charge capacitors to VDD, which is their max capacity. So you have two capacitors C1 and C2. You charge both of them to their maximum capacity. Step 3, let Q equals 1, Q bar equals 0. Let us assume the current contents of Q and Q bar are 1 and 0 respectively. This is just an assumption we are going with. You can also assume vice versa, Q to be 0 and Q bar to be 1, and the working will still be the same. I would encourage you to work it out after you understand the basic procedure. I would encourage you to pause the video and work out the different combinations. Anyhow, coming back, let Q equals 1, Q bar equals 0. Now, this is the current state. This is what we want to read now. We want to read the value of Q. We haven't read it yet. Inside the circuit, at the location Q, 1 is stored. At the location Q bar, 0 is stored. But how do we read that and get it out through the bit line or bit complement line? We are going to see that. Now we know Q is 1 and V equals VDD at M5. Now at this point, Q is 1, meaning this part is high and this capacitor is fully charged. So this part is also full or high, and this one is also high, meaning the charge is full or high in both cases. So there will be no flow of charge because there is a high here and a high here. But Q bar is 0 and V is VDD at M6. So Q bar is 0 and V is fully charged at this point. So what did we just see? At this point, this line is a high and this capacitor is also fully charged. So there is no difference in the voltage between these two spots, this spot and this spot. Whereas when we come here, this Q bar holds a 0, meaning this spot has 0 voltage or 0 charge. And this capacitor is fully charged, meaning this is high and this is low. So there is a potential difference between these 2 points. So what happens? The capacitor starts discharging. Charge starts flowing from here over here. So the voltage across bit complement decreases. So let me explain this again. This is low, this one is high. So charge flows from C2 to this point, and bit complement represents the charge associated with the capacitor. So if this one is going to start giving out charge, then the charge or the voltage associated with this area decreases, right? So the voltage across bit complement is going to start decreasing. Whereas at this location, the voltage associated with bit remains whatever it was. There is no change because there is no flow here. Now we connect these two, bit and bit complement, to something called a sense amplifier. Sense amplifier is a circuit component to which you connect B and B bar, or bit and bit complement. And what does it tell you? It tells you the final output depending on these conditions. If the voltage across bit complement is reducing, then the output is a 1. If the voltage across bit is reducing, the output is a 0. This is the standard convention. So here we saw that the voltage across bit complement is reducing. So it will give me the output 1. And what was the initial value stored here? It was a 1. So I have successfully read the data which was stored in my setup. So let me give you a quick recap of the read operation. First of all, we set the right line to be a 1, thereby turning on the access transistors, indicating that the operation is going to take place with respect to this cell. Now I charge both capacitors to their maximum capacity. Now I assume there is a 1 here and a 0 here. Because this is fully charged and this is also high, there is no potential difference between these 2 points. So the voltage across bit line remains as such. Because this is a low and this is fully charged, there is a potential difference. To bridge that, the charge starts flowing from C2 over here, meaning bit complement line is its voltage is reducing. Now I connect both these lines to something called a sense amplifier, which will give me the output based on this condition. If B bar's voltage is decreasing, the output is 1. If the voltage across B is decreasing, the output is 0. Here we saw that B bar's voltage is decreasing, so the output it gives me will be 1, which is exactly what was stored over here. Now if this had been a 0 and if this had been a 1, if you work out along the same lines, you will realize that this one's voltage will remain constant, this one's voltage will start decreasing. Again you send both to the sense amplifier. According to this condition, it will give me a 0. So while reading from an SRAM cell, this is how I read Q, which is the value stored in it.